Okay, let's study the details about the criteria for a good estimator. The first criterion was about the center of the sampling distribution. So the mean should be correctly centered at the true parameter. To think about this, first let me define the estimation error in this way. Theta hat is your estimator and theta is the true parameter. So the difference is the error, right? If it's 0, you are correct. Your estimator is correct. But remember, theta, the parameter is constant. Parameter is not random, but the estimator is random. So the estimation error is also random. Or you may think it this way: when you repeat the estimation with different data, then each time your error may be different. Maybe in one trial you may get a negative error, but in another you may overestimate. So it can be different. So overestimation, we say you are an estimator is overestimating the parameter if the error is positive, and underestimation is when the error is negative. So it's clear, but again, it is random. So we take expectation of the random error. So estimation error expected value can be written in this way. Expectation does not affect the constant because remember, it's another linear transformation. Random variable is theta hat, and we are subtracting minus theta. And when you take expectation of this, minus theta is preserved like this. So anyhow, the expected estimation error is called the bias. So on average, your estimator is this much different from the true parameter. So if the bias is positive, that means the estimator tends to overestimate. So if the bias is bias is positive means your estimation error is on average positive, which means this is greater than the true parameter. Estimator is greater than the true parameter. So you are overestimating. If the bias is negative, underestimating. And the best is 0. If the bias is 0, the estimator is said to be unbiased, which is what we want. This is the first criterion. So we want an unbiased estimator. And graphically, I already explained blue estimator is unbiased, but orange estimator is positively biased, or so it's overestimating, has a center greater than the true parameter. So it shows the concept of unbiasedness. This was the first concept, and it's quite intuitive and important. It's easy to understand. The average has to be correct to avoid overestimation and underestimation. And the second criterion we consider is the efficiency. It's a little bit more complicated, and it is about the variance, or I would use standard deviation. They are equivalent. Like standard deviation is the square root of the variance, so it's easy to translate between them. And standard deviation of an estimator is called the standard error, right? So it's exactly it. It tells you why it's called standard error. When you estimate something, you will have error. Now, how much is the standard distance, standard error? How much it's away from the true parameter? And that process exactly the same as calculating the standard deviation. So you may understand it as a special standard deviation in the context of estimation. And suppose that, imagine if you repeat estimation with different random sample, and so you have you have two estimators. So using the same method but with different data, you calculated the estimator and you get two numbers, two estimators. If the standard error is large, these two results can be different. But if the standard deviation is small, the two results will be consistent. For example, put it this way. Excuse me. You are estimating the presidential election. And so first, today I surveyed 1,000 people, and my result is that the candidate of interest is leading 10%. And tomorrow I surveyed 1,000 people again, a different set of 1,000 people, but tomorrow I got different results, like the candidate is losing 10%. So yesterday the result was leading 10%, but next day it's losing 10%, which means it's very unreliable. Something is wrong. So this is reflected in the standard error. This happens when standard error is large. So each time, even if you are using the same method, but the results may be very different depending on the data. So it's not desirable result. So you want the standard error to be small. The standard error should be small so that the estimator is reliable. And in statistics, we say one estimator is said to be more efficient. One estimator is more efficient than another if its standard deviation is smaller. So, it's a typo. 2 should be inside parentheses. So, the estimator with the smaller standard deviation is more efficient. Its efficiency is relative criterion. So, so you are comparing two estimators. It cannot be zero. The standard deviation cannot be zero. When standard deviation is zero, that means there is no randomness, which means you are just choosing one number, whatever data is. So it's never a good estimator. Then what is the minimum? How small it can be? That's very difficult to answer. There is an answer theoretically, but that involves more math. So I'm not saying I will not tell you about that, but the concept is the relative size of standard error. So in this case, blue has smaller standard deviation, so it's more efficient. And when I was a student, I wondered why its name is efficiency. Like I would say reliability, which makes more sense. But again, it's not my fault. The textbook defines it as efficiency. Every textbook uses the same term. Then I understood. I understood it recently, like many years after I was a student. When I learned it, the idea is the efficiency is determined by, usually the standard deviation is determined by the sample size. Remember, in the previous chapter we learned if your estimator is the sample average, then the standard error is this one, which is given by this. So clearly, the standard error is inversely proportional to the square root of the sample size. So as the sample size increases, clearly the standard deviation decreases and your estimator becomes more efficient. So that's one thing, it's obvious, but this comparison is quite unfair. You cannot compare two estimators using different sample sizes, right? But when you have the same sample size, then now it's a matter of efficiency because you are comparing two estimators in terms of their standard errors, and that means which estimator is using the sample more efficiently. So their sample sizes are the same, but which is more efficient, which extracts more information from the sample so that it's more reliable. So I guess this is why this criterion was named as efficiency. And for example, even if the sample size is the same, the standard error of the median is about 1.253 times larger than the standard error of sample mean. So when you compare sample mean and sample median, sample mean is more efficient. So right, and because sample mean uses the data more efficiently. That's how I understood the naming. And simple graphical summary, visual summary. Suppose that there is a target. There is target, and you are using 4 different guns, rifles, and say you shot five shots, and the best result is this. All of the 5 shots are within yellow circle, the inner circle, and it's correctly centered around the bullseye, and it does not deviate much. It's within tight to each other, close to each other. So the rifle is well like set. How do I say? Anyhow, it does not move around too much. And in this top right example, the problem first is that it is biased. So it's centered at here. You should aim at this point, bullseye, the yellow, but it looks like it's aiming at green or like a black or blue. So something is wrong first, but good thing is they are close to each other, which means at least if you reset the aim at this point, and it'll be very good, right? It's the only problem here is it's stable, reliable, but it's going somewhere else, deviating away from the center, the correct aim point. And the bottom left tells you that it's correctly centered at the bullseye. So on average, it hits the average of the 5 points. It's more closer to the true center, but the problem is it's unreliable. You are aiming at the correct point, but even if you aim at the correct point, but it deviates. Your result deviates from your aiming point. So it's unbiased in the sense that the center is correct, on average correct, but it's inefficient. It's moving around, unstable. And this is the worst. Bottom right graph is the worst because it's aimed at a wrong point and it's unstable. It's moving around. So it summarizes what we learned in this chapter. And I'm going to show you simple examples in the next video, and I'm going to finish the lecture in the next video. The next video may be short. Thank you for watching. See you later.